you just like listen to his voice, you can understand which questions were going to be on the exam and which one. So it was like you knew what to study.
Okay.
But it's still like, I don't know, it's not that hard. But it is.
Okay, here.
Classes. So
Hi everybody, happy Monday. We're starting, we're going to be discussing Stewart section 3.2 today, which is inverse functions and logarithms. So I'm going to start by just introducing the idea of an inverse function. I'm going to start by, before doing that, talking about one-to-one functions. So here are the words. F, so function F is one-to-one. What it means is the following. If you have two x values that are not the same x value, then the resulting y values are not the same. So let me give an example. F of x equals x squared. Oh, and I should say more. I should say graphically, no horizontal line touches the graph more than once. That's the so-called horizontal line test. So this function f of x equals x squared is not one-to-one.
Don't you mean the vertical line?
Nope. The vertical line test is a requirement for a function to be a for a graph to be a function. Horizontal line test, there's more than one horizontal line test. This horizontal line test is the test to determine if a function is one-to-one. So let's look at the graph of y equals x squared. It passes the vertical line test because it is the graph of a function. But look at this horizontal line, y equals 4. It touches the graph here at 2, 4, and it also touches the graph here. So observe that minus 2 is not equal to 2, but minus 2 squared is equal to 2 squared. That is, f of minus 2 is exactly the same as f of 2. So this function is not one-to-one. I can feed in two different x values and get the same y value. On the other hand, f of x equals x cubed is one-to-one. So if I look at the graph of y equals x cubed, there is no horizontal line that touches that graph more than once. So, definition of an inverse function. So if you have a function f with domain A, capital set A, Now remember what domain is. Domain is the set of numbers that I can feed in as x values that will give me a y value. So that's the domain, denoted by some letter capital A. And this function has a range capital B. That's the set of numbers that actually come out. So if a function has that domain in that range, and if f is 1-to-1, then there is a function called the inverse function. And it's denoted by the symbol f with a superscript -1 that has domain B and range A. So whatever the domain of the original function f is, that's going to be the range of the function f inverse. And similarly, whatever the range of the original function f is, that's going to be the domain of the inverse function. And that has this property. So, if I'm going to sell you a function, I have to tell you its domain, to tell you its codomain, or I have to tell you its range, and then I have to tell you how the function acts. So I have to tell you, if you feed it something as input, what's the output going to be? So if I feed this function input, it's going to be something that lives in this set capital B. So things that live in this set capital B, I'm going to denote using the letter little b. So f inverse of little b, this is little b is in the set capital B. What's going to come out is this letter A. Now that's something that comes out of the f inverse function, so that's going to be something that's in the set capital A. Well, I haven't told you. I just showed you the letters I'm going to use to represent these things. But I'm going to do this. This means that f of A equals B. So in other words, if I feed a little b into f inverse, I'm going to get out the letter A that has this property. If I feed that little letter A into f, I get out that b. So in other words, the x, y coordinates of points on the graph of f inverse are going to be interchanging the x, y's of the points in the graph of f. So b comma a is on the graph of f inverse. That's an x, y, that's an x value, and that's the resulting y value. That only happens when a comma b is on the graph of f. So for example, f of x equals x cubed. We've seen this example before. This graph has the point 2, 8 on it. Now the inverse function is this function. f inverse of x, that's the cubed root graph. That's x to the 1/3 power. And it goes through the point 8, 3. So 8, 3 is on this graph. 8, 2 is on this graph. 2, 8 is on the graph of the original function. Inverse functions they obey what are called the cancellation equations. So they say this: f inverse of f of a equals a for all numbers little a that are in the set capital A, that's the domain of f. And there's another cancellation equation that says this: if I take a number little b that's in the set capital B, and I do that to it, and then I do this, and then I do this to it, I get my little b back again. This is true for all b in set capital B.
Hey, Mark.
Yeah.
On that top equation, it looks like you wrote f prime of f of a.
Thank you. F inverse of f of a is a. Okay, now I just gave you an example of a function and its inverse function. Just said this is the inverse function. But in general, there is a procedure for finding the formula for an inverse function. So procedure for finding the formula for the inverse function. The inverse function is denoted as superscript. So you start with a formula for f of x. So we have y equals f of x. And that's going to be given as some expression involving x. Well, all we do is we solve that equation for x in terms of y. So we're going to solve the equation for x in terms of y. So the result will be x equals some new expression involving y. Well, that new expression involving y is f inverse of y. That new expression involving y is f inverse of y. That is x equals some new expression involving y, and that is f inverse of y. And then there's an optional step. You know, you're going to have some expression involving y. That expression is your inverse function with y as the variable. Some people don't like having y as a variable. They like having x as a variable. But we're used to the idea that variables can be different letters. We've used t as a variable. We've even had functions where there is no variable. We just have an empty function. So I'm going to say optionally, we can change the variable in the expression for f inverse to whatever we want. So let's do an example. Let's let y be, or let's let f of x, right? F of x be this function. 4x minus 1 over 2x plus 3. So the fact is, this function is one-to-one. You can do that, you can figure that out a couple of different ways. The simplest way might be to just graph this on Desmos. And you see that it passes the horizontal line test. So A, find the domain of f. B, find the range of f. C, find the formula for f inverse. D, find the domain of f inverse. And E, find the range. So 5-part question. All right, I'm gonna go over here. I'm gonna start working over here. Now, this is all prerequisite material, so I'm gonna skip some stuff. But I'm going to tell you what I'm skipping, so you can do it at home. So look at that formula over there for f of x. F of x equals 4x minus 1. I'll just write it again. 4x minus 1 over 2x plus 3. Can anybody tell me what the domain of this function is and why? I have one hand up. Let me pose the question in a different way. Remember, the domain of a function is the set of x values that will give you a y value. So are there any numbers that would not give you a y value using this formula? I've got one hand up and I've got one head nodding. Can I get some more heads nodding? Can anybody spot a bad x value that would not give me a y value? What could go wrong when you're trying to compute a y value?
Is it is 1 and 1/4?
No, 1/4 is okay. If x is 1/4, I would get a numerator of 0. The denominator would not be 0, so I'd get a y value of 0, which is perfectly good. But what could go wrong would be
negative 1/2 on the bottom.
negative
One half, or 1 1/2.
negative 3/2. So the domain is all numbers except -3/2. See, if you plug in x equals -3/2, I'd get 0 on the bottom. What's the range? Well, this question is sometimes harder to answer. So I'm going to put a little question mark here, and we'll come back to this. Let's go on to C. So leave some space. C. We're going to try to find the formula for F inverse. So y equals f of x. That's 4x minus 1 over 2x plus 3. So according to that plan, we're going to solve for x in terms of y. So the result is, you do this at home, or in the library. The result is x equals 3x plus 1 divided by 4 minus 2x. So that baby right there, that's F inverse. I'm sorry, x equals 3y plus 1 over 4 minus 2y. Sorry, 3y plus 1 over 4 minus 2y. So that is F inverse of y is equal to 3y plus 1 over 4 minus 2y. So that's this business. We just did this. We solved it. We didn't. I did. Now, I said earlier that optional step would be you could change the variable. So optional change of variable. I could write F inverse of parentheses would be 3 times parentheses plus 1 over 4 minus 2 parentheses. Or I could say F inverse of t would be 3t plus 1 divided by 4 minus 2t. Or I could use the variable x. F inverse of x is 3x plus 1 over 4 minus 2x. So that's part C. Part D, remember, was to find the domain of this new F inverse function. F inverse of x, I'm going to go ahead and use the version that has that x is the variable. 3x plus 1 over 4 minus 2x. Okay, can anybody look at that formula and tell me what the domain of that formula is?
Is it all numbers but 2?
All numbers except 2. Because if I use x equals 2, I'm going to get a 0 in the denominator. So the domain is all numbers except 2. Oh, remember that the domain of F inverse is the set that's the range of F. So we can go back here. The range is all numbers except 2. So one way to get the range of the function is you solve for x in terms of y. you get the inverse function, you figure out what's the domain of the inverse function, and that tells you what the range of the original function is. Now, that seems like a lot of work. There's another way of looking at this function that will maybe help you understand why that's believable in a simpler way. If my formula for the function was just y equals 4x over 2x, what would the y values always be? 2. Just be 2. So that perfectly good fraction there would give me y values of 2. When there's a 4x on top and there's a 2x on the bottom, I'm going to get y values of 2. Except in the dorky case when x is 0, then this would be undefined. Now take that perfectly nice fraction that gives y values of 2 and mess it up. I do something different in the numerator from what I do in the denominator. So the numerator is never going to be twice the denominator, because I take this thing where the numerator is twice the denominator and I mess it up. So this fraction is never going to equal the number 2. And so that's a way of looking at this and realizing I'm never going to get a y value of 2. Now look at this. Let's go back to E. What's the range of F inverse? Well, I've got to look at this and think, well, if this expression were 3x over minus 2x, my y value would always be negative 3 halves. That perfectly nice fraction would give me y values of negative 3 halves. But I mess it up, I do something different in the numerator from what I do in the denominator, so I'm never going to get a y value of negative 3 halves. So the range is all numbers except negative 3 halves, which is the set that was the domain of the original function. So it's pretty cool that you can look at these in that way and figure that out. All right, I want to check one of the cancellation equations. So we hope that if we do this calculation, we get that as an answer. Remember that's a property that inverse functions obey. If I take an x and I feed it into f, and I get f of x as a result, and I feed that into f inverse, I should get back to where I started. Well, let's check. So f inverse of f of x, well, I have to start by getting the formula for f of x. F of x is that thing, 4x minus 1 over 2x plus 3. So I've got to compute this. Well, to do this, it would help to go get the empty version of f inverse. That thing. Let's write that down first. So that means I've got to do this. 3 times parentheses plus 1 over 4 minus 2 parentheses. That's how f inverse eats its parentheses. It does that to them. And then I've got to put that thing in all those parentheses. 4x minus 1 over 2x plus 3, and 4x minus 1 over 2x plus 3. So that's the expression for f inverse of f of x. Now look, there's just a whole bunch of arithmetic here. You know how to do this, you got to just grind this out. I'm going to put dot, dot, dot. You do this. But trust me, if you do all this, you do get x. It does work. Okay, now we want to talk about meeting part 2, which is derivatives of, derivatives of inverse functions. All right. Here's a big if. There's a lot of stuff in this if. So if f is a one-to-one function, now remember the implication of that. If I have a function that's one-to-one, I know that there exists an inverse function. But I'm not done with the if. If f is a one-to-one function and f prime, I should say, f of a equals b. So that's just telling me a point on the graph of f. And f prime parentheses a is a number, it exists, and is not 0. That's a whole bunch of stuff, a bunch of ifs. Then, f inverse prime of b exists. So this is telling me that the inverse function has a derivative at b. And it's given by this formula. F inverse prime at b is 1 over f prime at f inverse b. In other words, it's equal to 1 over f prime at a. All right, so why does this make sense? Well, for one thing, it might not make sense. I don't remember much from my freshman year of college, but I do remember that this confused the hell out of me. So I never really understood this at that point. Why is this believable? Well, let's suppose that we have a graph f of x. And it has a point a comma b on it. So f of a equals b. And let's suppose that I have this tangent line here. And the slope of this tangent line is f prime parentheses a. Well, this function is one-to-one, so there exists an inverse function. And remember that the inverse function graph is obtained by interchanging the xy coordinates on the graph of the original function. So f inverse is going to have the point, instead of a comma b, it's going to have b comma a. Okay, just interchange those coordinates. And now look at the tangent line on this graph. This tangent line has slope. M is f inverse prime at b. It's the line that's tangent to the graph of f inverse at the place where x equals b. Now look at the slopes of those two lines. In this picture, I should exaggerate this a little bit. This is a pretty steep line. So my delta y is pretty big, my delta x is pretty small, so I have a pretty big number, that's my slope. Now look at this yellow triangle. Everything's been flipped over, so the number that was my delta y in this picture is my delta x. So delta x is pretty big, delta y is pretty small, so my slope is going to be pretty small. Delta y over delta x is going to be small. Main thing is, delta y over delta x is going to be 1 over the delta y over delta x over there. So that's why this yellow number, f inverse prime at b, that's that yellow slope, is going to be 1 over the red slope. So let's do an example. F of x equals 2x cubed plus 3x squared plus 7x plus 4. That function is known to be 1-to-1. So the implications of that are that this function has an inverse function. So find f inverse prime at 4. Notice we're not asked to find the formula for f inverse. We're just supposed to find that particular derivative. So we're going to use that formula. So f inverse prime at 4 is 1 over f prime at f inverse of 4, whatever that means. Okay, well, let's just get to work on finding the pieces of this. So I'm going to do this over on the side. So leave that equation. I'm going to come back to that and continue working there. So we have to figure out what f inverse of 4 is. Now remember what this means. I'm trying to figure out the number that makes this true. F inverse of 4 equals some number. But that means that f of that same number has to equal 4. That's how the inverse function is defined. If I have an x-y pair on that graph of f inverse, that means that if I reverse the coordinates, I get a point on the graph of f. So we're looking for the number that has this property. F of that number equals 4. So can anybody think of a number that has the property that f of that number equals 4? 0. If I plug in x equals 0, I get 0 plus 0 plus 0 plus 4. I get 4. So notice f of 0 is 0 plus 0 plus 0 plus 4. So that's 4. So I found one x value that causes f of x to be 4. So here's a question. Are there any others?
No,
Why?
because f of x is a one-to-one function.
Exactly. F of x is 1 to 1. So I have found one x value that will give the y value of 4. F is known to be 1 to 1, so there can't be any other x values that give the same y value. So this is the only such x value. So that means that f inverse of 4 is the number 0. So that symbol there stands for 0. So I have to do 1 over f prime, parentheses 0. So all of this stuff here was us just trying to figure out this step. We had to, here I had to figure all that stuff out, and that just came back and we put a 0 there. Okay, well now we need to figure out what f prime 0 is. Well, to do that, we need to figure out f prime of x. So can somebody tell me, somebody who's been lurking and hasn't answered or really wants to answer and make some big money, what's f prime of x?
Uh, 6x squared plus 6x plus 7, and that's it.
Great. I'll pay you later. Thank you. All right, so now for the big money, double your money. What's f prime 0?
7.
Yeah. 0 plus 0 plus 7, so it's the number 7. All of this stuff was us figuring out what goes here.
Hey, Mark,
So this is 1 over 7.
you forgot to put the squared on the first 6x.
Oh yeah. Thank you. So we just found that the line that's tangent to the graph of f inverse at x equals 4 has a slope of 1 over 7. Let me graph this really quickly, because this picture looks a lot like the picture that I drew over there. We have just observed the graph of f goes through the point 0, 4. So this is f of x. And the tangent line, when it goes through this point, has a slope of 7. And the inverse function goes through the point 4, 0. F inverse of 4 was the number 0. And we just found out that the line that's tangent to that graph at that point has slope m equals 1/7. Isn't that pretty? So notice we never found a formula for f inverse, for the inverse function. I don't even know how to do it. I mean, it can be done. There's a procedure for finding the inverse, the formula for the inverse function of a cubic. I think. Gabriel probably knows this. He's younger than I am.
I definitely do not know that.
So, but even without knowing the formula for f inverse, we're able to get the slope of that tangent line. Somebody's phone has a really cool ringtone, way better than mine. Can you turn it off? All right. Going back and forth here. We have 10 more minutes. Logarithmic functions, meeting part 2. So this is all supposed to be reviewed, but I think it's important that we go over it in this course, because as I've mentioned before, students are always fuzzy on exponents and logarithms. So oh, before I forget, remember, you all remember when my office hours are, right? When are they? Right after this class. Good. I'll be hiding, but you can find me. But you know that all the TAs have office hours as well. Gabriel has 3 office hours. I have 3 office hours per week. Kingsley has 3 office hours per week, and Othniel also has 3 office hours per week. So that's 12 hours per week of office hours. So make use of those. Those office hours are all on the web. You can go to any of those office hours, any of the TAs, not just Gabriel's, not just mine. You can go to Kingsley's and Othniel's office hours as well. All right. So recall the exponential function y equals b to the x. It has domain all real numbers, and has range positive numbers, and it contains the points 0, 1, and 1b. Let's make a graph of this function. Y equals b to the x. It goes through 0, 1. It goes through 1b. That's because b to the 0 equals 1, and b to the 1 equals b. And furthermore, it has a horizontal asymptote at y equals 0. Now, pertinent to today's discussion is, notice this. This graph passes the horizontal line test. It's 1 to 1. It's a 1 to 1 function. There is no horizontal line that touches that graph more than once. So we know that the inverse function exists. Now, I'm going to be dramatic here, and I'm not going to spill the beans. I'm not going to tell you the name of this function yet. I'm going to tell you all the things that we know about this function. Actually, you're going to tell me some of this stuff. What's the domain? What's the domain of the inverse function? Got one hand up. Any more hands up? Yeah.
0 to infinity.
Yeah, so I'm going to say it's all positive numbers. And what's the range?
All real.
All real numbers. And what are 2 points that are on this graph?
0 or 1, 0, and 1.
So it contains points 1 to 0 and b, comma 1. Well, I'm going to make a graph of this. It contains 1, 0. It contains b1. All those other points are flipped. So that horizontal asymptote becomes a vertical asymptote. X equals 0. Notice the range, the domain, the x values that will give you y values. This is the positive x's. And notice the resulting y values, all real numbers can come out as y values. This function is called the logarithm function, base b. So this is the exponential function. with base b, and this is called the log function, logarithmic function with base b. And it's denoted this way, y equals log with a subscript b of x. So notice what this graph tells us is that log base b of 1 is equal to 0. That's because b to the 0 equals 1. And we see that log base b of b is equal to 1. b comma 1 is on this graph. And that's because 1 comma b was on this graph. Furthermore, we have these cancellation equations. We have log base b of b to the x is just x. That's true for all x values. Any x value that you want to use will work. But this is a little different. B to the log base b of x also equals x. But this is only true for positive x's, because I have to have an x that I can feed into the logarithm function. This is for all positive x. Now, a special case is base b is the number e. This is the natural exponential and the natural logarithm. So we have y equals e to the x for the natural exponential, and for the natural logarithm, instead of log base e, we just say ln. So this is y equals ln of x. So this graph goes through 0, 1, and it goes through 1 comma e. This graph goes through 1, 0, and e, 1. So you see that ln of 1 is 0, and ln of e is equal to 1. And you get the cancellation equations. That is ln of e to the x is equal to x, and e to the ln of x is equal to x. All right, so there's more stuff in the book in this section. There's stuff about the limits of these. Notice that the limit as x goes to infinity of this graph is infinity. This graph is going up. Whereas the limit as x goes to 0 from the right is negative infinity. So there's some problem involving limits with these functions. I would have liked to have gotten to those today. There's a lot of things I would like to have gotten to. We just finished a little bit over 1 page of notes. I had 3 pages of notes that I usually thought we could do. But this is actually, I was already talking really fast. So I'll stop here. If you haven't signed in, the sign-in sheet is up there.